See that, I believe. And all right, introduction to the analysis of variance. So what we'll do today is we'll explain the purpose and logic of analysis of variance. We'll perform analysis of variance on data from a single factor study. We'll know when and why to use post tests. We'll compute Turkey's HSD and Sheffield post hoc tests. We'll compute N2 to measure effect size. Tools you'll need, you want to make sure you know about variability, some of the squares. Remember, some of the squares is literally squaring all your values and then summing them. Sample variance, degrees of freedom, introduction to hypothesis testing, the logic of hypothesis testing, uncertainty and errors in hypothesis testing, and independent measures of the t-statistic from chapter 10. So for analysis of variance, this is used to evaluate the mean difference between two or more treatments or populations. This uses sample data as the basis for drawing general conclusions about populations. The clear advantage over a t-test can be used to compare more than two treatments at the same time. A typical situation in which ANOVA would be used is shown right here in figure 12.1. 3 separate samples are obtained to evaluate the mean differences among 3 populations or treatments with unknown means. So here we have our sample, n equals 15, m equals 23.1, and sum of the squares equals 114. Sample 2, n is 15, the mean is 28.5, sum of the squares is 130, and the sample 3, n is equal to 15, the mean is equal to 20.8, and the sum of the squares is equal to 101. Some terminology in the analysis of variance. You have a factor, that is the independent or quasi-independent variable that designates the groups being compared. You have the levels of the factor, that is the individual conditions or values that make up a factor. Then of course you have factorial design, a study that combines 2 or more factors. Then we have the null hypothesis. The treatment conditions have no effect on the participant scores in the population. This is equivalent to saying that the group means do not differ from each other. This is, in a sense, the null hypothesis is all the means are equal to each other, no variance. Don't let the word ANOVA freak you out. That's analysis of variance. So a null hypothesis, there's at least one mean difference among the populations. The treatment conditions do affect the scores. The acceptable shorthand is not null hypothesis like this. The issue, how many ways can the null hypothesis be wrong? All means are different from every other mean. Some means are not different from others, but other means do differ from some means. Some means are not different from others, but other means do differ from other means. So why use the ANOVA if T can compare 2 means? Well, experiments often require multiple hypothesis tests, each with type 1 error alpha level. Type 1 error for a set of tests accumulates test-wise, the alpha to the experiment-wise alpha to the test-wise alpha. The ANOVA evaluates all mean differences simultaneously with one test, regardless of the number of means, and thereby avoids the problem of inflated experiment-wise alpha. Test-wise type 1 error and experiment-wise type 1 error rate are sufficiently complex concepts that you may want to really reflect on. The test statistic for ANOVA, it's not possible to compute a sample mean difference between more than 2 samples. The F ratio is based on variance instead of sample mean differences. Variance is used to define and measure the size of differences among sample means or the numerator. The test statistic for the ANOVA, variance is in the denominator measures the mean differences that would be expected if there is no treatment effect. F is equal to the variance differences between sample means, the F differences expected with no treatment effect. The logic of analysis of variance. Between treatments variance, variability results from general differences between the treatment conditions. Variance between treatments measures differences between sample means. Within treatments variance, the variability is within each sample. Individual scores are not the same within each sample. Figure 12.2, the independent measures ANOVA partitions or analyzes the total variability in the 2 components, variance between treatments and variance within treatments. That's what we're looking at right now. Just think about this conceptually. Yes, I totally have a worksheet that will walk you through the steps in terms of what an F score is and how to get there. And I will put that in this lecture or the lecture following it. and I might extend the deadline by another day or two, just so you have a little bit more time to study. I'll probably do that realistically. So the total variability between treatments variance, systematic treatment effects, random unsystematic factors. This is the numerator of your F ratio. Your denominator is your within treatments variance is random unsystematic factors. That is your denominator of the F ratio. The F ratio, the test statistic for ANOVA, 1 of 3. The F ratio can be calculated after we have analyzed the total variability into 2 basic components. F score is equal to the differences including any treatment effects, differences with no treatment effects. The denominator of the F ratio is called the error term that measures only random and unsystematic variability. The value obtained for the F ratio determines whether any treatment effect exists. There are 2 possibilities. No systematic treatment effects. The differences are entirely caused by random, unsystematic factors, or the treatment does not have an effect and causes systematic differences between samples. All right, and continuing on. The F ratio, if the null hypothesis is true, the size of the treatment effect is near 0. The F ratio is near 1 and indicates that the differences between treatments are random and unsystematic. If the null hypothesis, however, is true, the size of the treatment effect is more than 0. The F ratio is noticeably larger than 1, and there are systematic treatment effects. So let's decide if each of the following statements is true or false. True or false? ANOVA allows researchers to compare several treatment conditions without conducting several hypothesis tests. True or false? If the null hypothesis is true, the F ratio for ANOVA is expected on an average to have a value of 0. So true, several conditions can be compared to one test, and false, if the null hypothesis is true, the F ratio will actually have a value near 1. So some ANOVA notations and formulas. The number of treatments is K. The number of scores in each treatment is N1, N2. Total number of scores is N. When all the samples are the same, N is equal to Kn. The sum of the scores for each treatment is equal to T. The grand total of all scores in the study is G equals sum of T. No universally accepted notation for ANOVA. Other sources may use other symbols. This is the structure and the sequence of calculations for the ANOVA. First, you do the F variance between treatments and the F variance within treatments. Each variance in the F ratio is computed as the sum of the squares over degrees of freedom. Then you do the variance between treatments, the sum of the squares between the difference degrees of freedom between, and the variance within treatments is the sum of the squares within and the degrees of freedom within. To obtain each of the sum of the squares and degrees of freedom values, the total variability is analyzed into 2 components: the sum of the squares total, sum of the squares between, and sum of the squares within. Degrees of freedom total, degrees of freedom between, and degrees of freedom within. Partitioning of the sum of the squares for the independent measures of ANOVA. The sum of the squares total, you have the sum of the squares between treatments and sum of the squares of the treatment means, and the sum of the squares within treatments, the sum of the squares inside each treatment. Analysis of the sum of the squares. The sum of the squares total is this formula. The sum of the squares within treatments is this formula, and the sum of the squares between treatments is this formula right here. And no worries, we're going to do some exercises in this lecture or the next, which will be posted today. The analysis of the degrees of freedom. The total degrees of freedom total is equal to n minus 1. The within treatments degrees of freedom within is equal to n minus k. Between treatments degrees of freedom between is equal to k minus 1. Partitioning degrees of freedom total n minus 1, degrees of freedom between treatments k minus 1, and degrees of freedom within treatments, the sum of n minus 1 is equal to n minus k. No worries, I have worksheets and Excel actually too, which walks us through that, which we'll walk through. You also want to remember these formulas: the calculation of variances, the MS and the F ratio. MS is equal to this S squared between sum of the squares between and the difference between. MS within is equal to S2 within SS within divided by degrees of freedom within. F is equal to the sum of the squares between divided by the sum of the squares within is equal to MS between and MS within. Don't worry if you don't understand all this right now. Again, there's worksheets coming up. Learning check. Analysis of variance produces a sum of the squares total is 80 and the sum of the squares within is 30. For this analysis, what is the sum of the squares between? 50, 110, 2400, or more information is needed. The answer is 50. Again, just today, this lecture, think about what I'm saying conceptually. We are going to do a worksheet on F scores. So examples of the hypothesis testing and effect size with ANOVA. If the null hypothesis is true, the value of F will be around 1. Because F ratios are computed from two variances, they are always positive numbers. The table of F values is organized by 2 degrees of freedom. Degrees of freedom numerator between shown in table columns and degrees of freedom within shown in table rows. The F distribution of F ratios with the degrees of freedom is 2, 15. Of all the values in the distribution, only 5% are larger than F equals 3.68, and only 1% are larger than F equals 6.36. An example of hypothesis testing and effect size within ANOVA. Hypothesis tests use the same 4 steps that have been used in earlier hypothesis tests. Computation of the test statistic F is done in stages. Compute the sum of the squares total, sum of the squares between, and the sum of the squares within. Compute the mean of the squares, the total mean of the squares between, mean of squares within, and compute F. We will do a worksheet on this. Then you're going to get this awesome chart, which we're going to walk through. So don't even sweat it if it doesn't 100% make sense yet. So you have a concise method for presenting ANOVA results. Again, ANOVA is analysis of variance. Helps organize and direct the analysis process, convenient for checking computations, standard statistical analysis program output. Table 12.4, this is an ANOVA summary showing the results of the ANOVA calculations for the data in example 12.1. Don't get lost in all the formulas. The idea is to get to the table of the goal of the process, and I'm going to break it down for you in small steps in that worksheet coming up here. Like I said, this lecture or the next one. Measuring effect size for ANOVA, compute the percentage of variance accounted for by the treatment conditions. In the published reports of ANOVA results, the effect size is usually called N2 ETA squared. R2, a concept of the proportional variance explained. N2 is the sum of the squares between treatments over the sum of the squares total. Treatment means and standard deviations are presented in text, table, or graph. Results of ANOVA are summarized, including F and degrees of freedom. The p-value, N squared, for example, it would look like this. F 215 equals 716, P is less than 0.05, and is squared is equal to 0.488. Assumptions for the independent measures of ANOVA. The observations within each sample must be independent. The population from which the samples are selected must be normal. The population from which the samples are selected must have equal variances. Homogeneity of variance. Violating the assumption of homogeneity of variance risks invalid test results. Post hoc test. ANOVA compares all the individual mean differences simultaneously in one test. A significant F ratio indicates that at least one difference in means is statistically significant. This does not indicate which means differ significantly from each other. Post hoc tests are follow-up tests done to determine exactly which mean differences are significant and which are not. Post test and type 1 errors. Post hoc tests compare two individual means at a time, which are pairwise comparisons. Each comparison includes a risk of a type 1 error. A risk of a type 1 error accumulates and is called the experiment-wise alpha level. Increasing the number of hypothesis tests increases the total probability of a type 1 error. Post hoc post-tests use special methods to try to control experiment-wise type 1 error rate. Tukey's honestly significant different test. This is a single value that determines the minimum difference between treatments, means that is necessary to claim statistical significance, a difference large enough so that P is less than the alpha experiment-wise honestly significant difference, HSD. HSD is equal to Q divided by the times the square root of MS within N. The Sheffield test. The Sheffield test is one of the safest of all possible post hoc tests, protection from type 1 errors. This uses an F ratio to evaluate the significance of the difference between any two treatment conditions. FA versus B, the mean of the squares between the mean of the squares within, calculated within the sum of the squares of the two groups. Which combination of factors is most likely to produce a large value for the F ratio? Large mean differences and large sample variances, large mean differences and small sample variances, small mean differences and large sample variances, small mean differences and small sample variances. Your answer is large mean differences and small sample variances. Decide if each of the following statements is true or false. True or false. Post-tests are needed if the decision from an analysis of variance is failed to reject the null hypothesis. True or false. A report shows ANOVA results. F227 equals 5.36. P is less than 0.05. You can conclude that the study used a total of 30 participants. First one, false. Post hoc tests are needed only if you reject the null hypothesis, indicating that at least one mean difference is significant. Second one, true. Because degrees of freedom total is equal to n-1, and because degrees of freedom total is equal to degrees of freedom between plus degrees of freedom within. More about the ANOVA. The numerator of the F ratio always measures how much difference exists between treatments. The denominator of the F ratio measures how much difference exists within treatments. This is figure 12.7, which is a visual representation of the between treatments variability and the within treatments variability that form the numerator and the denominator respectively of the F ratio. In A, the difference between the treatments is relatively large and easy to use. In B, the same 4-point difference between treatments is relatively small and is overwhelmed by the within treatments variability. The relationship between ANOVA and t-tests. For the two independent samples, either T or F can be used. Always result in the same statistical decision. The T statistic compares distances. The F ratio compares variances. The relationship is F is equal to T squared. For any value of a critical region, T critical squared is equal to the F critical. Figure 12.8, the distribution of T statistics with the degrees of freedom is equal to 18, and the corresponding distribution of F ratios with degrees of freedom 1, 18. Notice that the critical values for alpha are 0.05, and T is equal to plus or minus 2.101, and F is equal to 2.101 squared, which is equal to 4.41. Here are your formulas again. So you have your formula for some of the squares, degrees of freedom between treatments and within treatments, and your F ratio right here. We're going to, like I said, walk through this in a moment here on some worksheets, which I'll record and get posted. So there might be a delay, but I should be able to get that posted today for you guys. If there's questions on equations, concepts, reach out to me, 786-879-0179. You can text, call, or email me, jk.mack@ferrum.edu. Hope that this lecture was helpful. Hope you learned something. If not, this should have provided the basis, at least conceptually. And I will see you in the next video. Take care.